Hello friends, today we are going to see the concept of thermal forces developed in rail. Right. So in previous videos we have seen that LWR, so let us say this is a LWR. So LWR was divided into three parts: breathing length portion, central portion or non-breathing length portion, and breathing length portion. Right. So we have seen that in breathing length portion the stress increases from 0 to maximum 0 to maximum. So in this video we will see how this stress varies. That is, so when temperature goes above Td by 1 degree, then what is the maximum stress developed? When temperature goes by 10 degrees above Td, what is the maximum stress developed? Right, we will calculate. And we will also calculate when temperature falls by below Td by 10 degrees, what is the stress developed? So all these things we will calculate. So what is the maximum stress developed in LWR track with respect to temperature? Those things we will calculate in this video. So to start with, so we know that E is equal to stress by strain. So stress is equal to modulus of velocity E into strain. So once you know E and strain, you can calculate stress, thermal stress developed in rail. Right? Once you know stress, you can calculate thermal force. Right. So to calculate strain, we know that delta L is equal to alpha L delta T. So this Td minus T I am taking presently as delta T. Right. So delta L is equal to alpha L delta T. What does this mean? So let us say you have a rail of length L, and now you are increasing temperature by T degrees. Now you are increasing the temperature of this rail. Now because of temperature, the rail will expand. Let us say delta L is the increased length of the rail. Now this increased length delta L is given as delta L is equal to alpha L delta T. So delta L is equal to alpha L delta T. T is change of temperature, that I will see in next slide. So alpha L delta T. Now if you take this L here, what happened? Delta L divided by L is equal to alpha delta T. Right. So this delta L by L, this delta L by L is called what? Strain. Change in length with respect to original length is called what? Strain. Right. So here strain is equal to delta L by L, which is equal to alpha into delta T. Now you know E and you know alpha delta T. Now you can calculate stress. Okay. So see here, stress is equal to E into strain. So stress is equal to into delta L by L, which is equal to E into alpha delta T. Now you know that stress is equal to force divided by area. So force is equal to stress into area. That's what we have done here. So stress is equal to force by area, which is equal to E into alpha delta T. So F is equal to AE alpha delta T. So this is thermal force, this is thermal stress. So this is the final equation to calculate what? Thermal force. Right. So thermal force is equal to area of cross section of the rail into modulus of velocity into alpha into delta T. So if you know A, if you know E, if you know alpha and temperature change, you can calculate thermal force generated in rail. Right. So for 52 kg rail and 62 kg rail, these are the values of A, E, alpha, delta T. So A mean A of 62, area of cross section is 66.15, and for 60 kg it is 76. Modulus of velocity is 2.15 into 10 power 6, and for 60 kg also same. And for 52 kg alpha, coefficient of thermal expansion alpha is 1.152 into 10 raised to minus 5 per degree centigrade, and for 60 kg also same. So you know A value, E value, alpha value, and unknown parameter is only temperature change, and once you substitute this, you can easily calculate this force developed. So I want to calculate the value of thermal force for 52 kg and 60 kg. Right. So what is the formula? F is equal to A E alpha delta T. So now let us take Td is equal to 30, and at side now temperature is 31. Okay, 31 degree. Now what is delta T? 31 minus 30, which is equal to 1 degree. So this I have taken as 1 degree like this. Right. Suppose one more thing I will tell. Suppose TD is equal to 40 and temperature at site is 45. Now delta T is what? 45 minus 40, which is equal to 5 degree. So that's what I have taken, right? So now substituting in our equation, F is equal to A alpha delta T. A is 66.15, E 2.15 into 10 raised to 6, and alpha 1.15 into 10 power minus 5. You get this value. How much? 1638.4 kg, which is equal to 1.638 tons. Similarly, for 60 kg, substituting all its values, area of cross section, modulus of velocity, and temperature, alpha value and temperature change as 1 degree. For 1 degree, you are getting this much, 1.9 tons, right? So finally, what you got? For 52 kg rail, 1 degree rise of temperature above TD, you are getting 1.6 tons of force, thermal force. For 60 kg, same, for 1 degree rise of temperature, you are getting what? 1.9 tons. Right. So like that we will calculate for 10 degree, 20 degree, 30 degree, what is the thermal force generated. So see here. So at TD you have stress 0 in 52 kg and 60 kg rail. Okay. And now TD plus 1 degree above TD, you are getting what? 1.638, 1.903. You have calculated, you have seen previously. Now TD plus 10 degree, what you have done? Simply multiplied this with into 10, this into 10, you have got this. 1.6 into 10 will give 16, 1.9 into 10 will 19. Now TD plus 20, how much you got? 32. Just simply multiply with 20, so you have to remember these two values, 1.6 and 1.9. If you remember this, you can calculate the thermal forces generated in rail at any temperature, above TD. So what you have seen from this table, so as temperature increases, okay, stress also increasing from 0 to maximum. Okay, and one more thing, see, this is above TD, temperature is above TD, so whatever stress developed is compressive. So when temperature increases above TD, the stresses developed in rail was compressive in nature. So these things you have seen. Next we will see this next slide. See, this is TD minus T. It means what? TD 0 0 0. Now this is TD minus 1, means what? Let us say TD is equal to 30 and at site you have seen temperature is 29. Now delta T is how much? 30 minus 29, which is equal to 1 degree. Temperature is falling below TD. So when temperature is 1 degree, you got this much, right? 1.63, 1.93. Previously also same, but this is tensile in nature. Tensile. Previous one is compressive in nature. So when temperature falls below TD, you are getting tensile forces. When temperature increases above TD, you are getting what? Compressive forces. So this is tensile forces. TD minus 10. So same into 10, 16.38 into 10, 19.03. This value into 20, you got this much, right? So here also what we observed, as temperature is falling below TD, tensile forces developed in the rail also increasing. Okay, so you have seen this like this, right? So when temperature is increasing, compressive forces are increasing. When temperature is falling below TD, tensile forces are increasing. That's what you have seen. So now you can calculate compressive forces and tensile forces developed in rail at any temperature, right? So overall, what have you seen? So in 52 kg rail, right, above TD, okay, above TD, for every 1 degree you have 1.6 tons of thermal force and 1.9 tons of thermal force in 60 kg, right? And you also seen that when temperature was above TD, forces are compressive in nature, and when temperature was below TD, okay, you are getting what? Tensile forces. Okay, compressive forces, tensile forces, and for 1 degree rise 1.6 tons and 1.9 ton. So these things you have seen, right? So now you can calculate this force. So what is the maximum force developed in LWR track for every 1 degree rise of sun temperature above TD? Okay, so TD plus 1 degree, what is the stress developed? TD plus 20 degree, what is the stress developed? TD minus 20 degrees, what is the stress developed? TD minus 30 degrees, what is the stress developed? You can easily calculate this. Okay, thank you so much friends. Thank you for watching this video. Please do subscribe.